Okay, so yeah, today I wanted to talk a bit about asynchronous output or async IO in Python. If you also happen to code in JavaScript besides Python, you probably encountered the two very famous keywords async and await in JavaScript. And actually, Python has something similar to that, but it's maybe a bit less known. So maybe just a bit of theory for starters. What is async IO? As you know, when you want to speed up your program, one of the options you have is that you can run things in parallel. So you can use multiple CPUs or multiple cores to process data or do something in parallel. And async IO is sort of a different approach to this problem that's suitable for a bit of a different situation. So in async IO, it almost seems like you are doing things in parallel, but it's not the case. In async IO, what you are doing is that if, let's say, one part of your code is waiting for some data, say from an API that you are accessing through network, while one piece of code is waiting, you can actually run some other piece of code. So this is the basic idea of asynchronous input-output, that instead of waiting, for the API to respond, in the meantime, you can run some other piece of code. And it's very useful, as the name suggests when there is some wait time for some input or output. So one example is the APIs, external APIs over the network, but this can also be used when you are connecting to a database and doing something with the database, and you are waiting for the database to handle your query, or sometimes it's even used when you are opening files and stuff like that. So the thing or the interesting thing is that basically there is no parallel execution. There is still only a single thread in your program. The program still uses only one CPU, but it can make your programs faster by not waiting for input and output, and executing something else in the meantime. So let me show you a sort of a hello world example for this. I actually prepared it this morning. So this is, I can make it a bit bigger. Okay. So this is a sort of a very basic example of how async IO works in Python. So just as JavaScript, actually Python from some version 3.7 or something like that. It's pretty old. Has these two keywords, async and await, that allow you to work with async IO. You can define, or the first thing you can do is you can define asynchronous functions by using the async keyword in front of the def keyword. And technically speaking, this is called this is no longer a function. It's called a coroutine. When it has an async keyword in front of it. And
sorry, can I have a question?
Yeah.
The async IO is directly in the Python, or do I need?
Yes. The module, I will talk about it. It's directly in Python. You don't have to install it, but I will get to that. Yeah. So you have this. You actually don't have to import the async IO module to use the async and await keywords. So they are just part of the syntax. And here what I'm doing is that I'm defining a very simple coroutine that prints some like hello statement, and then what it does, like in this hello world example, it's using asyncio sleep, which basically simulates some sort of waiting. You can imagine that instead of having a sleep here, we can have like an API call. We might be talking to some external API here instead of that. And as you can see, there is like this await keyword in front of the asyncio sleep call. And what this await keyword tells Python is that, okay, at this place, this function basically does something I need to wait for. So once you basically hit this line during execution, this function sort of goes to sleep until this little piece of code is resolved. And while this function is quote unquote sleeping, some other function can do its job instead of it. So that's the basic idea. And once like this sleep ends, once this thing we are waiting for is done, the function can then again continue, and a bit of a typo here, and execute the rest of the functions. So this is sort of the basic idea. There is this thing called event loop at the background that's actually taking care of synchronizing all your asynchronous functions or coroutines. It basically takes care or monitors which functions can be run while some other function is waiting and stuff like that. So basically, it's sort of like a director that decides which part of your code is currently running, depending on all these await things. It monitors like which functions have to wait, which can run, and stuff like that. So in this demo, I have this asynchronous function, and I also created like this main function or coroutine. And it's using this utility function from the asyncio module, which someone already asked about. So asyncio is directly in Python. You don't have to install it. It's available as is, and it offers many different functions that help you work with this asyncio paradigm. And one of these functions, besides sleep, that we already used, is the gather, which basically allows you to start multiple asynchronous functions at once, and basically then this gather waits until all these functions are executed. So and then what I do, when I am running this as a script, I use the asyncio module again, and it has a run method that basically allows you to run any asynchronous function. And this piece of code is basically synchronous. So basically, what's happening here? If you have had some like normal code here, after this asyncio run, basically everything, all your async stuff would execute first. You would basically need to wait for all the async stuff to execute here, and then you would run like normal code afterwards if you had something more there. So this like run function basically makes things synchronous again, like at the higher level. Okay, so if I run this code. And again, I will make it bigger. So it was hello Py. What we can see here is that if you look at the order of the print outputs here, and compare it to the code. Maybe you have noticed this high function has like this number parameter, and I set it to 1, 2, 3, just to have an idea like which of these 3 instances of the function that I have here in gather is currently running. And as you can see, what's happening is that first, all of the three functions print like the first print statement here before like the await call. Then all of these functions go to sleep, and or I think it's more precise to say that after the first function prints this high from 1, it goes to sleep. Then, since this function is waiting for the sleep to end, the second function can execute, and it prints its first print statement, and again goes to sleep, and then needs to wait. So there is room for the third function to print its print statement. Then all three functions are asleep for a while, and then at some point the first function awakes. Since it went to sleep first, it should also awake first. And it can then continue the execution after the await statement and do the second print or execute the second print. Then the second function awakes, and or the sleep ends for the second function, and again the execution can continue, and the second print statement executes, and the same thing happens for the third function. And if you would run this like in a synchronous manner, and you use like the normal time sleep function and executed these functions or called these high function 3 times in your normal code, you would basically have to wait 3 seconds, right? Because there are like 3 sleep calls, each basically forces the computer to wait for 1 second. And if you run it in synchronously, one statement after each other, it would take 3 seconds. But if we run, or if I use time here, I can actually see that it takes a bit over 1 second for this function to execute. So it almost seems like things are happening in parallel, but again, there is like no parallel processing here. There is a single thread, and basically what it does is while one function is waiting, other function can execute in the meantime. So these are sort of the basics, and I am going to give you a bit of a demo. How is this actually useful in practice? So what I've prepared here is you probably know Flask. Flask, if you don't know Flask, is a very simple library or framework for creating web applications in Python or websites. And it works in a very simple way. You create a new application, and then you use decorators to assign functions to different paths when opening the website in your browser. So in this case, there is just a slash, so it's like the index, the main path of your website. And what this function is doing, it's just to demo the communication with some external API. I'm using the Hacker News API to get the latest post on Hacker News, and then find the author of this post in the second call. So yeah, first I get basically this first call gives me the ID of the last post that was posted on Hacker News, and the second call gets detailed information about that post, and I'm specifically interested in this by field. It returns a JSON, and that's transformed into a normal Python dictionary, and it has this by key which contains the name of the author. In the main function, I simply then run the application on some port. That's all what this is doing. And if I execute it, so I can just run it like this. And in my browser, I can actually go to 5000, right? Go here, and what you can see that the latest post on Hacker News was posted by someone whose nickname is ZFG. So this is a very simple implementation, simple web app that just prints the latest the user that posted the latest post on Hacker News. And what we can do here is that we can check how long it takes for this web server to respond to requests. I discovered this beautiful utility AB. I think it's something like Apache benchmark or something like that. And what I can say here is that I want to execute, let's say, 300 requests, 100 requests in basically at the same time. So the C stands for concurrency or concurrent requests. So how many requests should be released or issued at the same time to my website. And then I just put in the URL that I want to test. So in this case, it's my localhost URL like this. I run it, and it's benchmarking the web page. And there is a lot of stuff, but what we can, for example, check that the entire test took 4.5 seconds. So this is a synchronous version written in Flask. And now let's have a look at, I also have an async version, which is written in something called Quart. Quart is something like an asynchronous version of Flask. It's actually from the same group of people that developed Flask. They also created Quart. And you can see that the code is very similar to the synchronous version, except, of course, instead of using like Flask, we are using Quart as the name. We also set up like a root, and we have like an index function, but now we are putting the async keyword in front of it. Now it's like asynchronous function or coroutine. And the second thing that's different here is that instead of using requests like we are doing here in this Flask example, request is a pretty famous library for Python that can help you do HTTP requests. We are using AIO HTTP, which is an asynchronous HTTP client. So it allows you to run asynchronous HTTP requests. And there are a few interesting things in this code that you can actually do with this asynchronous IO. The first thing is that you can create asynchronous context managers. So you can put the async keyword in front of the with keyword in Python. And basically, what we are doing here is we're creating a new HTTP session, let's say. And then in this session, we are again calling the URL for getting the last item, the latest, the ID of the latest post on Hacker News. And yeah, this library uses a lot of context managers, a lot of with statements. But in the end, here we are extracting the post ID. What's interesting here is that we are using like this await keyword when we are accessing like the .text method. This is similar to request. Request also has like a .text. I think it's not a method but a property to extract like the textual text from the HTTP response. And then once we have the post ID, we do a second request on the URL that contains the information about the specific post, and again extract the by field, which contains the name of the author, and just return it. And then we just run the code or run the app, and that's it. And let's do that. So I will stop the synchronous app and start the synchronous app. It runs on the same port, and it does the same thing. So if I go to the browser again, if I reload it, now there is a new port by someone called Black Puppy Dog. And what's more important for us is what our benchmark will look like. And if you run it and look at the time taken for tests, it's 3 seconds. So we were able to cut the time by 1.5 seconds, basically by just not blocking the execution while we are waiting for the Hacker News API to respond. So basically, as I said at the beginning, we are executing 100 requests at the same time. And what this code does is, since it's all asynchronous, while we are, for example, waiting on this session get statement here, so while we are waiting for the data from the API, other function can actually or other request can be served. Okay, so we can basically we don't have to wait until we receive the data and block other requests. Basically, since we are waiting here for the data to arrive, we can serve other requests in the meantime. And so this can cut down like the response time and basically help you handle many more parallel requests in your web application. So this is just a very small example. Yeah.
Can I have a question? Because in this very example, the second request is basically depending on the data from the first one. So I'm wondering, why is this particular case actually faster?
Yes. Well, the thing is, okay, you say that your let's say you have two requests that arrive to you at the same time. One of the requests or that you need to serve. One of the requests, for example, gets here at this to this point, and while basically or at this point we are accessing some external URL, we need to wait for it. And while we are waiting here, the other request can actually start, or we can start processing the other request and basically do the same thing. So we can create this variable with the latest URL and issue this request, and then again wait.
So it's not asynchronous just with, between those two, but also between the request from.
Yes. In this case,
okay.
it's more about processing multiple requests in an asynchronous way.
Right.
Yes, like you are right that in this case, like inside this one function, basically everything executes in order, and you indeed have to wait for the first request to finish, and then you can release the second or do the second request on this like on the second URL afterwards. You have to wait for the first part to finish, for the second part to start. That's right. But while we are waiting, other like requests issued to you, like to your web server, can be handled in the meantime. So that's the game here. Yeah.
This is actually better example than I thought. Thank you.
Yeah, so this is sort of the gains that you can get using async.io, and like running a web server is only one example. I think you can also use this, I don't know, when you are writing like some sort of a web scraper, where you need to scrape multiple websites, you know, like in the traditional way, you analyze the HTML code and extract URLs, and then you follow these URLs and so on. And there is a lot of wait time, like between. It takes a long time for the web page to actually load, to get the HTML of the web pages on the links that you are following. So basically, this helps you speed up things like web scraping. That's let's say a second application. One thing that I am also experimenting with in one of my side projects is, I don't know if you have noticed, but actually all these AI LLM providers have a pretty bad uptime. If you look at the statistics, it's like 99.6% uptime, which is not that great given today's standards. So in one of my side projects, what I'm doing is that I actually, when I have some LLM use case, some AI use case, where I need to talk to some like OpenAI or Anthropic model or something like that, I actually issue multiple requests to different providers at the same time, and then basically the first one that responds is the one that I will use. So it's sort of like a backup if one of the or one request fails. If let's say one service is not available, I can use the response from some other LLM without additional waiting, because both requests are being processed at the same time. Of course, it's a bit more expensive, but
Yeah.
If let's say redundancy and response time are important to you, this might be an interesting use case. So yeah, that's it. This is what I wanted to show you today.